The first question, so again, what I want to talk today about is a method that takes a sequence and predicts where in this sequence you have an interaction interface to another protein. You do not know the binding site, you do not know the structure. That's the idea. So that's when the method should work. Now, where would I get the data for this from? And in principle, what we want to distinguish here is external heteromers, so transient protein-protein interaction. In this particular case, the GP100 against the antibody. So that's what the binding site we want to find. Hey! Okay, I believe I have to. The trouble is I forgot my leash. So it's an old firewire cable that hopefully will do the job. Hey! Yes. Now we have. Come. Sorry. Let's see. I need somebody with good advice how to tie a firewire cable. Yeah, that's a computer dog. But he cannot even lie down, huh? Well, he can lie down. Okay. So back to the task. We want to predict where this protein binds to another protein in a transient interaction. So transient essentially means it goes on and off. Okay? So the question is, how do we extract the interaction? So where do we get them from? Where would you get interactions from? So we want to see residues that bind in transient protein interactions. What type of experiment gives you that? Those data. Any idea of a database that has data like this? What do you see there? Protein structures, right? What's the database of protein structures? PDB, the protein data bank. So it contains at this point about over 100,000 structures. That's more than 100,000 proteins because they come in multiple units. And this is an example. So this is one particular entry, and I missed this PDB identifier, it's written somewhere. So in this particular PDB entry, you have this entire complex. Okay? So you also, in fact, have the subset of the transient protein interactions here. Overall, essentially, we in 2010 we had 65. Again, we have over 150,000 proteins at this moment. When 6 years ago we had 3,000 complexes in there. So this is a large number. Now, how do I get a data set? For that data set, what I have to do, I take the entire PDB, then I have to sort of look at a sequence unique subset, and then do a sequence unique subset against the PDB. Well, I don't have to really do that for the entire database, but only for the proteins for which I have interaction data there. And then I get these, and I showed you that. Those came, in fact, from the question, is it significant? I showed you in a way in which we can show that it's significant. But now, the question really is, what is it that I use as a threshold for defining contacts? And this is one particular answer here. So I essentially extract in the PDB file all the atoms, and then I say whenever the blue and the green are at least some distance from each other. Now, what is the minimal number of a distance that you would? They must be further apart than what is the smallest number you can? I mean, 0 is not the smallest number. What sort of is the smallest number you can think about where to put this? If I told you the threshold were to be put, so I show you 6.5 angstrom, so 0.65 nanometer. But if I were to tell you 1 angstrom, what is there that is sort of 1 angstrom that you know of? Do you have any molecule that you know is roughly the size of an angstrom? Water is water, the radius of a water molecule. So water molecule is 2 angstroms. So that is clearly too small. Now, if I told you something like 15 angstrom, what is that? You know anything that is like 15 or 20 angstrom? How big are very, very tiny proteins? Any idea? Anybody, any idea? Any guessing? If I told you a protein is 1,000 angstrom, you would be happy with that? So 1,000 angstrom is in the ballpark of, so nanometer, this is 1 angstrom is 0.1 nanometer, so that would be 100 nanometers, so it's 0.1 millimeter. No, this sounds bad, right? So this is a protein. You could actually see it, so that cannot be true. So it must be clearly something much smaller than 1,000. So in the ballpark of 20 small proteins sort of sit. This is also way too big. With 20, essentially, you get all residues in some proteins. So we need something in between. How can you find something in between? How can you sort of, if your supervisor typically gives you a number, say the supervisor doesn't give you a number, how would you do it? Well, you would Google, right? And see what people have done this sort of thing, what did they take? Now, say you can't find anything in Google. What would you do? Say you were the first to work on that.
What's the average distances?
From what?
From the whole protein.
So you take essentially inside of the green, you look at all the residue to each other. But this is not quite the problem. That would be one way of doing it. And that clearly would define something such as, so an average, how far is it to reach any point in your protein, right? That would clearly define the sort of nonsense level. So this is clearly too high. This is a good way. So, but to your first point here, just go and measure. This is what I want. But actually what we have to measure is really between two interactions. Right? And so, say we now how do you believe if I plot the distribution for all the red and greens, how do you believe this will look, this distribution? So somehow I have an angstrom axis here. So essentially I look at the blue protein and I look at every single atom in the blue protein and I ask are all the other atoms in the green protein. How do you believe the distribution will look? Well, clearly, so let's just, I don't have two colors, but if these two proteins would bind like this, and I take every single one, say the max is somewhere here, right? Maybe this is a little bit longer, the way I draw it. But so there will be a maximum somewhere. The maximum will be given by the two most distant points on the two proteins, right? And then you will see that, in fact, what we ultimately are after is this binding site here. But clearly, if I look at everything, then it will be dominated by the things that, most of the things you find will be somehow further away, will be outside of the interaction site. Right? Say this is 20% of the residues, so 10 to 20% or 10 to 25% or 30% is the type of number of interaction residues that you typically have, ballpark. So then you immediately see that most of the residues here will pair to most of the residues here, and they will not have anything to do with the interaction, right? And they will be somehow far away. So there will be, again, Teresa's idea of an average. Let's just put the average in the middle of the protein. So most from this density will map here, and then we'll get a peak here. Okay? Now, then we will have a tiny set of things that are very close to each other. And those are the interaction sites. So that is my observed distribution. It's not a Gaussian. I have to point this out clearly here. It clearly will not be a Gaussian. It will be asymmetric. So this side here will be steeper than the other side. So, how do I choose my threshold from that curve? One thing is clear, the majority here is not what I'm after. But this is sort of, again, in a way that Teresa may have implied, we can keep away from the average, right? So we could say that clearly my threshold has to be well below this number. Question remains, what is well, and how much does it have to remain below? So the next problem is that unless I saw a dip here, which in fact we don't see, so the dip would give it away. Now, then I would say, that's the binding site. But unfortunately, we don't see a dip. And that brings us to the next issue. So it brings us to the issue that now we have the data, but we still can't do it. The data doesn't tell us. Now, if we replot this here, if somebody, for some proteins, labeled the binding sites, and for some interaction pairs, you could easily imagine that somebody can do that. You, as an expert, labeling whatever they consider as the interaction site. You could label them through energy function. And now, in that particular case, you would most likely get something that is pretty much a Gaussian. And say this is the average here, the mean, in terms of angstrom. Now this is the subset of touching sites, labeled in red here. Now where do I put the threshold? Yes, sorry.
No.
I'm sorry. So if that were to be in front of you, now where would you choose the threshold? So again, let me repeat. Now what I'm drawing here is the subset of, somebody labeled all the subset of blue and green that bond, that bind. That somebody, sort of an expert, says they are binding sites. And for them I see, again, this is the distance, the angstrom distribution here, and M is the median of this sort of pretty much Gaussian. Where do you put the threshold? You want to machine learn, essentially, that these three residues here are binding in a transient protein-protein interaction. That's ultimately what you will do, right? Here's the question, where do I put the threshold to say which ones bind? Well, in this particular case here, you have them labeled, so you have an expert done it. But the expert will not do that for 3,000 or whatever the number is. So you can only learn the distribution, or you can only learn something about what is a good threshold. So what could you do? Where do you put it? Obviously, nobody in this room knows. Just go forward and guess. And again, so in your work you will encounter many of these decisions. And in many of these decisions you will not be able to really say this way or that way. What is important is that you find a way afterwards to check whether it's right. And that some of those decisions are as good as you can. Science is about doing new things. So you will constantly face the same situation that you're in now. Your value system does not give you all the data you need. Yes?
What exactly are you plotting? The energy of the between two residues?
Not really the energy. I'm looking at the distances. So you see what I hypothesize here is 3 different interacting pairs, and they have different distances. And I have some expert, could be you, just looking at the interaction, label the ones that you argue on the screen interact. And now I plot what are the distances that I see. So on the screen you can pretty clearly see, let me go back to an example like that, you can pretty clearly see what interacts well in a higher, if you really plot them as spheres, you can somehow see that. And then you get a distribution, and that's the distribution of the ones that an expert said interact. Okay? So where now, an expert has done that for a few proteins. How do I put the threshold that in this particular case is 6.5? Say the answer to my question is 6.5, but I don't have numbers here. Where's the 6.5 on my plot? Somewhere. See what? Yeah, it is there. What do you mean by that?
I think at the far right. So.
Are you happy with that?
Yeah.
Okay. Is anybody saying it should be different? If nobody says it should be different, then I want somebody else to argue why it's there.
I just wanted to say maybe one could also look at the distribution of the non-interacting residues.
Yep.
Like
That doesn't have-
where it overlaps and then.
Unfortunately, that doesn't help us. So that's the point I made before, but you were not in the room. No, but you are not in the room, so you cannot know. And in fact, I'm very happy that you say that. So my logic is right. The question comes up if I don't show the other one. So that distribution doesn't help us. This is the binding distribution. Simon says put it somewhere here. I mean, plus minus. This is not really the point. Somewhere to the right. But Simon says not M. Let's just let's call that the point R, and that put the point L. So why not M? Simon is right.
We discard a lot of binding residues that are really binding residues.
Well, that would be the explanation here for L. So if you took L, then you limit your data set badly. So you believe that is the distribution of all the binding residues. You take the cutoff here. Essentially, you take only the very, 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 very strongest. And if you have a very huge data set, maybe that's enough. But otherwise, that could be dangerous. But that is not quite the reason for the M. For the M, in fact, you could argue that compared to the L, the M already gains half of all my binding residues. Why not M? Yes?
The last time you didn't choose the M in another curve, I don't know what the topic was, he said that in M the error is the biggest.
That's the issue. Can somebody else explain to me why that would be the case? I don't choose M because the error is the biggest. This is technically correct, but it does not make sense alone if you leave it standing like that. So I need somebody else to fill in. Let's call it a reminder to find it in the memory banks. No? Nobody knows? So the point simply is, you make mistakes in the way the X-ray structure is. So it comes closer, it goes further apart. If you put your threshold into the max, then tiny mistakes here will have a maximal impact on the classification device. So you try to learn that there's a big difference between right and left of the threshold. But in the peak of the distribution, a tiny error in the experimental measurement may shift you over. In fact, many are affected around this threshold by a tiny mistake in the measurement. So if you put your threshold here into the R, the number of, say you have an epsilon mistake, for the same epsilon, you have much fewer errors that you make, right? That's also true for L, but the downside for L would be we have too few data points. So M is the problem that you're extremely dependent on the accuracy, and even if measurements would be more right, proteins move. So it's not even the experimental error, it's also the sort of when do you trap the interaction error. So M is a really bad idea. L has too little data, so we have to put some point like R. Now where exactly the point R is, unfortunately, is not very well defined. So there is some room for this. Okay, now we have the point. We have to parse the heavy atoms. Now we get to the next issue. How has any of you ever looked at a PDB record? In the PDB record, you have an atom, you have a residue, and you have something that is called a chain identifier. The chain identifier, essentially in a case like this, could be the protein. But it could also be something else. It could be the protein binding itself, could be homodimer, it could be a crystal effect. Because the proteins actually put them as a crystal, so they pack. And that could be the other chain. It could be a repetition of the same unit, or it could be that the homodimer forms, and you have to distinguish between these. And that is not that simple, but doable. And in fact, one way of doing it is you map PDB to Swissprot. In Swissprot, you see that the two things, what are two different chains in PDB, refer to two different proteins with two different sort of functional entities. And then you know that these are two different proteins. If it's referring to the same Swissprot record, most likely it's not, right? And that you do through an alignment method. So this way, we have a large data set. In this large data set, now we can actually, here's another issue. We can ask, to which extent actually, so ultimately what we want to do is finding this interface here means we want to, for instance, run a window-based approach. So we take, say, 9 consecutive residues, we run them through the protein, and we ask, in those 9, the central one, is that in a protein interaction or not? Okay? In order for this to succeed, I somehow, in this window of 9, have to see something about interactions, not only once. Ideally, I would have an interaction that, so this would work best if all of these 9 residues would somehow see the interaction. Okay? So the question really is to you, when you look at the interaction between two proteins, will they be of the type like this, where the interaction site here, this is protein A, this is protein B? Will they be like this? Or will it be more like this, A and B sort of wrapping around? So what I mean by this here, by the difference between these two doodles, is that in this one here, I have a relatively long local stretch that contacts, while here, the number of interface residues is identical, but I create them by sort of bulges, by strong bulges, right? So, meaning that the one involved in an interaction here may only be one. And these two here are very far away from each other. So in a local stretch of 9, I would not see that these two interact. Okay? So which of these two is more likely going to describe a protein interaction? Which of these two is more likely describing an enzymatic binding site? Do you know that? Let's call that model 1 and that model 2 here. Enzymatic activity. Is it 1 or 2? Nobody? Ever heard of a triad, histidine triad? So where 3 histidines come together from essentially far away. So enzymes are exactly, typically type 2. Now protein interacting with DNA, what is that? Have seen structures? of zinc fingers really going into the groove of the DNA. You have a long helix, so something that is relatively local but really sits entirely in the DNA. So this is really type 1. And what do protein-protein interactions for? How could you check? Again, you could Google, you could ask people, but if there were nobody around, what would you plot? Any idea? Am I too complicated today? Or is Christmas too far away? Or all of this. So essentially what we did here is the number of residues at the interface in a stretch of 9. So I simply take 9 consecutive residues, these 9, and I ask, in these 9, how many interface residues do I have at a given definition? So the definition we used here was 6.5. So we are redoing this at the moment, and we are choosing a lower threshold now. But anyway, and what I show here is in fact 2 answers. One for, in blue, the threshold being 6 angstrom, and in yellow, the threshold being 4 angstrom. And then essentially I do a distribution of all the data that I have. Okay? And in all of the data that I have, you see the yellow distributes here, the blue distributes here, but for both of those distributions, you see that there is more than 1 in a window of 9. So you have an aggregation. So the distribution here has both the yellow and the blue. So the yellow, we may say, has an average around 5, the blue around 6 or 7. Both are moved such that there's a significant fraction of the window, 9 consecutive residues, a significant fraction of that sees the interaction. Right? There are exceptions, but we have in fact a significant type of model 1. Now we have to do machine learning. So how do we choose the input features for machine learning? Okay, again, I have my data set. I want to predict which residue in a protein is involved. Input will be sequence only. Which residue is involved in a protein-protein interactions. So the simplest thing is, and again, please do that as often as you can. Ask the one who sits next to you. Ask somebody in the group. Go around, walk around. Science is communication, and a lot begins by you communicating with people. When it comes to the point where people react against you because you steal too much of their time, give back to them. Find a way to help them in return, whatever it is. Get them coffee or buy them chocolate, or it may sound funny, but you know, this may seal the deal. Just be nice in exchange for information. It really works very well often. Okay, so how do you choose the input? If the friend doesn't know it, the next in the group, so you walk around and all the chocolate doesn't buy you an answer. What do you do? Or coffee or whatever it is, the local currency. What would you do? Okay, we are beginning with an idea of, I want to look around 9 consecutive residues. There's a WeCap package. In the WeCap package you can try a bunch of machine learning devices. Weka from New Zealand. But ultimately what we want to do is we want to put into the system 9 consecutive residues, and we want to essentially train whether the central residue is in a protein interaction, a transient protein interaction, or not. And one way of doing that, we could have 2 output units, PP and not. And again, what's the simplest way to put the input feature? What's the simplest thing you can use?
Amino acid properties.
Yeah. The simplest, yes. No, that's not the simplest. What's the simplest? The amino acid, right? So forget about the properties. Property is an interpretation already. Don't forget that. We have a space of 20 amino acids, and very often the machine learning, by you not making assumptions, hydrophobicity, charge, it may help you, it may hurt you, but the most neutral way of doing that is simply the 20 amino acids. So in, for instance, a neural network, how many input units would you have? For this problem, if we want to code for 9 consecutive residues. It's very simple, with a tiny twist. So is that just refuse to talk to me, or is it really not? I'm totally removed from you, or is it yeah?
180,
so 9 times 20. That, here comes the tiny twist. The tiny twist is, now I want to slide this window through my protein, right? Say my protein has 1 to m residues. Okay? And my first question is, if that would be a residue 1, what are the full residues before it? So the simplest way of doing the 9 times 20 is essentially say I'm lazy, say we had only 4 residues, 4 amino acids, sorry. The simplest coding would be A, C, G, and T, just for the sake of the argument. And the simplest coding is, if it is an A, then this one is 1 and all the others are 0. That's the simplest coding, right? But again, how do I solve the problem that the first residue has something before it, and the something before it is nothing? How do I put that into my vector? Any idea? No idea? How could you do it? Is it too trivial, or? I need a break. Again, maybe we want to put in 9 consecutive residues. Residue, say, one way of doing that is that we have residue 42, 41, 40, 39, 38, 43, 44, 45, 46. And I want to predict ultimately this codes for, is residue 42 in a transient protein-protein interaction or not? So should this unit be on or that unit be on? And each of these points here is an abbreviation, or is a simplification for actually 20 input units. This is the 9 times 20, because there are 20 amino acids. And each one of these here could be a vector with 19 zeros and 1 1. Okay? So essentially what we have here is 9 ones and 19 times 9 zeros. That's my input vector so far. And all of that is fine, except for the moment that I want to predict the protein interaction state of the first residue. Because the first residue has four units above it, so 0, minus 1, minus 2, minus 3, and they're not amino acids. How can I code for that? So before the first residue, there is no amino acid, right? Sorry, Now it makes click. Now I still don't see how I could have. Okay. So once you try to predict for the first residue, the ones before it don't exist. This is the first residue. Okay. So how can I code for that? There is no residue 0. There is no residue -1. The protein begins, and that's the first residue. This is not chicken and egg. There's no beginning before the beginning. So how can we do that? Any idea? Well, one way could be to say, okay, the units before here, I just leave them all empty. So essentially in this particular case, I would then have 5 ones, and this is just going to be 20 times 4 zeros. They all stay 0. That's one way. The problem with that is that they all, with a 0 vector, whatever machine learning device you have, 0 is typically 0 times something, and 0 times something usually is not a lot. So this is like they are not there in some sense, and that could be misleading. So this is why people typically hack into a 21st unit, and that's the so-called spacer unit, meaning that is on when you are not an amino acid. So you invent the 21st amino acid, and the 21st amino acid is no amino acid. So then we still have 9 times 21, and it's still true that for every single example that I have, we will have exactly 9 ones in this game. Even if that's the first residue, or it could, for the sake of the matter, be the last residue. It's the same thing, except for then the spacers would be here. That much is clear, right? Now, the next question here is, then my neural network, for instance, will predict an output. So there's the P unit here, and there's the N unit. They're not P. And I have 2 different predictions here. In both of these predictions, I will say that it is P, because P is the largest, right? Now, here, the prediction is stronger than this. How can I use the strength of the prediction? Typically, we refer to that as a reliability. What can I use that for? Well, I can use it as a threshold. I could say, okay, I'm only going to predict if the difference is a certain number. Okay? And this is, if you're, we're going to go into ROC kind of curves where essentially I plot something such as accuracy versus coverage. So accuracy of all the ones at that threshold that you choose, that you predict, how many are right. Coverage is of all the ones that you wanted to predict, so that I know are right. How many did you find at that threshold? And this typically, you see a payoff. For some very, very few, you may have, you may have a higher accuracy, and when you want to predict everything, then you may have a low accuracy. And actually, I'm going to show you plots. Let me not confuse you. I'm going to show you plots where this is turned around, but it's symmetric, so it's the same thing. And essentially, dialing through this curve is what you can do through this threshold, adjusting this threshold. It then allows you, if you had a curve like that, it could in principle be that the curve you see is like that. No matter what the threshold, you always get the same accuracy. Right? It could even be a point. It could be there is no curve. It could be something like that. You always get the same accuracy, the same coverage. So how this will look has really to do with the way the training worked. And something like this is, in some sense, you could argue, a success. Because it also allows the user to pick a particular threshold and say, well, I will only focus on the ones that are predicted stronger because they are more accurate, for instance, right? Okay, now, in this particular case, we still haven't talked about what the input would be. So in the simplest thing, we only have amino acid sequence. Now, give me a better idea what we could put in. So 20 input units or 21 input units, just the amino acid identity. What else? So Teresa says, well, features. There may be, at least we may want to put in an additional feature such as charge, hydrophobicity. And the way we do that, so one way of doing that is, so we have 9 times 21. And then we would simply add, say, hydrophobicity, charge, maybe something, size. Size could be very important. So if I had only those 3, how many input units would I add? So I keep my 20, 21 to be on the safe side, and I want to add some new features. Those 3. For every single residue in the window, I want to add these 3. I mean, it's trivial. The answer is really trivial. Is it? I add 3 features. I add how many units? 3. That is if you could do that.
The size is not really trivial, I think.
The first is not really critical?
No, the size.
Ah, the size is that what you wanted to say?
It's not really trivial.
It,
I don't.
why would size matter? Is that what you're saying?
No. I mean, I don't think it's trivial to put it into the input vector.
What exactly do you mean by the word trivial? Reasonable?
No, it's not easy.
Oh, the size of a... Oh, okay. Let's just think about these 3 features as something that is binary. Charge, yes, no. Hydrophobicity, yes, no. Size, big or small. So I say big, so size would then be big. That would be the simplest one. But you're totally right. The size of an amino acid is not trivial. Actually, that gets in some sense into its solvent accessibility, if you want. And that, whatever. So this would be one way of doing it, right? We can refine from that. We can sort of have size classes. And size, again, we can measure an isolated amino acid, how much water can roll around, and that can define the angstroms, the square angstrom size surface of an amino acid. And this, obviously the problem here is that the amino acid being in a different connection, not all the surface will be available. So only part of the size will be visible for the protein interaction. But still, this may be something interesting, and that may be something you can do. Anyway, let's assume it's a binary thing. How many units do I add? Well, one way of saying it is, I will bring this additional information only for the central amino acid, then I add 3. And you could also say, well, charge is something, it's not only important whether the central one here is positively charged. It's also important whether there's a positively charged patch. Okay? So the overall sum of a positive charge may matter. And again, you could do that as a sum. That would be one way of doing it. Another way of doing it is you simply put 9 times 3 additional units. Right? What else could you use? What else do you believe will somehow matter for the protein interaction? Okay, let's form groups. Step forward and say something. Anybody has any idea? No? Nobody has no idea?
So, we can, for each amino acid, we can say if it's on the surface or inside the core of the protein.
Solvent accessibility, yes. I would add one way of doing that is here essentially add 9 units. Anything else?
Conservation.
We get back to that in a moment. Conservation. Yeah? Shoot, come on.
How big the side chains are, or the
Yeah, but-
spherical,
But you're funny. That's exactly what I meant by size. Oh, now I understand your question. Yes, that's a full circle. Yes, thank you. Yes, I believe this actually matters, and in some sense is related to solvent accessibility. But solvent accessibility. So solvent accessibility. I don't know whether anybody came to secondary structure. That's another way of doing it. Now, secondary structure and solvent accessibility. Where do you get it from? So for my PDB protein, I can read it off the SSP. But I want to predict for sequences for which I don't know the structure. Where do I get it from?
You can predict it.
Exactly. So we get a lot of prediction methods. Now this one here is sort of relatively simple, at least. You could say solvent accessibility is 1 unit. Secondary structure is a little more complicated. You most likely want to focus on HEL, so helix, strand, other. So this would buy you 3 units. So already this is 9 times 3. So now we're getting into adding a lot. But let's get to conservation. How can we bring in conservation? Teresa and Stefan, sorry. You came up with the idea. Do you have an idea? Well, you can just say it's conserved or not, or you can say somehow there are conservation weights. But the major input is still missing here. The major input essentially is the profile. Conservation could be 1 unit per 9, but the profile is not in it at all so far. And the great thing about the profile is really it does not add numbers. So the profile you can put into the same number of 9 times 21. The profile simply is you build an alignment for the family of that protein, and you ask, instead of having one of these here being 1, 1 and all the other zeros, 20 zeros and 1, 1, you just put the profile information in there, right? And you can get that right off PsyBlast or convert it to percentages. And that is in fact what this says. It creates a lot of overhead. You have to predict secondary structure, you have to predict solvent accessibility, and you use that all as input, and then comes this profile. The way you use the profile, this essentially, the protein sequence runs here. This is more than 9 at the moment shown here. The central one you predict, 1, 2, 3, 4, 5, 6. So it's 13 instead of 9 here. And you simply put for every single point here, you put in all of these, for all of these units, whatever you look up in the alignment. So in this particular case for the D, you have a D to 0.5. And so forth and so on. So you just see in the alignment what you see. So here it's a sort of 50-50 or 60-40. So you put 40 for the E and 60 for the I, and so forth, right? Again, in this particular case, for the simplest way, without looking at hydrophobicity and all of the other solvent accessibility, it would be, in our example, 9 times 21. You put it in the profile, okay? So in order to do that, you have to run a PsyBlast, you have to decide when the PsyBlast is done, you have to run secondary structure prediction, and all kinds of other things, and then you can predict it. And in fact, what helps most is the profile and the predicted 1D structure. Now we have to do cross-validation, so we have to take our training set, we have to hide under the table the test set. Then a random split is not enough, because we have to make sure that in the split between, sorry for the animation, between training and testing, there's no sequence identity. And we have to avoid overlap, as I said. Then we have to essentially look at the performance. The strength will be important, and then this essentially, if I only took sequence, that's what you get. That's the so-called rock curve, or rock-like curve. Only using sequence information. Coverage, so of all the sites the residue site is now a residue, I ask, how many of the residues have I observed to be in a protein interaction? And of those, at my threshold, how many did I find? And that's at my threshold of the ones that I predict, how many are right. And you see that there's a light blue up here. So for very, 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 very few, tiny coverage, you have very high accuracy. Very few translates to 1 per protein, 1 single residue. So in every single protein, you can find 1 residue at a very high level of accuracy, just using sequence. Now, my immediate question to you, do you believe this is random? So is this better than random, the blue? And just ends. So no matter what threshold you do, you can no longer find them. Is that random? Well, say, I wrote it down somewhere, that roughly every 5th residue, 20% of the residues are in protein interactions, right? Random would be ballpark 0.25, would be somewhere here, right? So it's clearly above that. Let me just show you a more sort of advanced random, would be this one here. And what I showed you before is in fact, now I have to sort of, I zoom into what I showed you before. So this is still the same thing, it's just blown up, okay? So it's tiny, tiny, tiny coverage here. And you see it's clearly above random. Not only there, but it's actually above random throughout. And one example shown here for one particular binding pocket, for very, very, very few, I can find the correct binding site. This is an example for that. Now, in order to go a level higher, I have to do all kinds of additional things. One is I have to do clustering. So I have to say that, well, if I see these isolated things, so if I see a window, after I run one prediction method, I know every binding site. And now, since I have observed this, I can say, okay, if I predict only 1 in a window of 9, I will just filter that out. Okay? Will only somehow accept according to the probability of this graph in some sense. The more complicated, a simpler one would be, I will only take if there are at least 3 or 4 or 5, whatever your threshold here is, in a window of 9. Everything else I will just erase. And that gives a refinement. The refinement is not shown here. And then I put the profile in. And that comes out when you put the profile in the secondary structure and solve an accessibility prediction in. So essentially this is using all the information, but the most important one really is profile and the 1D prediction. Again, random, sequence only, with profiles. So now the question becomes the ones that we see here. So previously there was 1 per protein in the light blue. Now we have several per proteins. Is there anything special? Have you heard of the concept of hotspots in protein interactions? Anybody heard about that? So the idea of a hotspot is really, let me see what it's explained here. A hotspot is a residue that is essential for the interaction. Now, one way, essential is a big word. How could you essentially define essential? Essentially, bless you. Any idea how you could define essential?
Without this residue, the interaction wouldn't take place.
That would be one. In fact, this is a very simple operational definition. So what I write here is knockout, and not only that, you can even measure it. You can even change every single residue and see, is the interaction still seen or not. Now we get into something that in the world of chemistry is very different than in the world of computers. And that is the way 2 molecules bind in chemistry. You remember this idea of there is a balance of states, right? You remember that if one substance A binds to substance B, protein A binds to protein B, then the binding is just the majority, the state that is observed most frequently. But there are moments when they're not bound. There are moments when they're bound stronger and weaker. And what we actually see is sort of a time point. And we will, if we push the system enough, we will see other points. We're not solving the interaction. So what essentially I mean is, maybe with this one residue exchange, even if that change one residue, turn it into alanine, for instance, and even if that were a hotspot, I may still sometimes see the interaction. Okay, so then you can say the hotspot is the one that knocks out the interaction most of the time, or most strongly. Another way of saying that is the hotspot is the one that contributes most to the energy of binding. Again, when I said 10 to 30% of the residues are involved in protein-protein interactions, this is a large number, right? This is 40, 50, 60 residues. And in some of those cases, something such as half of the entire energy of the binding is carried by one single residue. Now that's what people refer to as hotspots. And they are important for drug development, because this is what is targeted. If you want to have a drug bind to that protein, you're going to try to have the drug exactly in this sort of main binding site. If you want to avoid that protein A interacts with protein B, you want to put your drug into the binding site. And you want to first target the hotspot. Right? So that's why the hotspot is so important for that. Now some people argue hotspots don't exist, because ultimately, yes, we do see that some amino acids or some residues contribute more to the binding than others. But the counter argument is, if I sort it, so my residue 1 to say 30 residues involved in the binding interaction, and I looked at the energy contribution, then I see a function like that. Yes, there are some that contribute a lot. But ultimately it's just a function. There's nothing special to these that contribute a lot. There's nothing, they're not hotspots. They're not in a binary sense different. Okay? That's the counter argument. Because all of that is a scale, it's a sliding scale. Just like putting the threshold in terms of the distance cutoff, not at m, saying that there is a hotspot means you introduce a reality that in a chemical or biochemical way doesn't exist. It's the counter argument. Now, one way of addressing this, and this has been a debate for many years for biochemists, one way of addressing this is, if I could predict hotspots without training, well, then they must exist, right? So, what if these would be hotspots? Then my system has never learned hotspots. I taught, the machine learned simply to say that a particular residue is involved in an external interaction, a transient interaction. Yes or no. It never learned anything. I never put data about hotspots in there, right? So if it learned something about hotspots, then it can have only extracted that from a reality that exists. Okay? So one way of doing this, this is too fast, was you go again to the one sitting next to you, that's what Yanai did, and went to the group of Wayne Hendrickson. And Wayne Hendrickson's group, his friend Ashkenazi there, had done a large-scale study for the GP120 bound to CD4. And the ones that in fact sort of had hotspot-like qualities, that had a lot of impact on in the binding interface, are shown in red. That's experimental. The purple ones are predicted. So that's exactly when you go and pick only, I can't remember where he put the threshold, he just picked the top. Okay? And the very top is purple. The structure here is just shown for illustration. This was not actually used for the prediction. And you see that, here you already see that the purple and red have a very, very strong similarity. Here you see that sometimes you miss one here, this one is missed. Sometimes you over-predict. Here, this one is over-predicted. But overall, you get the patches right, overall this looks amazingly accurate. And again, the structure was not used for this prediction. Now, if you found that, would that be enough to publish? Say you published a paper, in the paper you said, this is my performance, I have a method that predicts protein interaction residues, the paper's out. Now you suddenly discover, actually, this is one of the I have to change the animation. One of the aspects of the very high ones. What do you do with it? And you have your result. It actually seems to be the case. What next? Can you publish that? It's a nice story, but actually it would be difficult to publish. I mean, since we were very early in this game, those days we may have, possibly could have even published it, but usually it's not enough. Usually you have to do something more. You have to establish that this is exactly true. Here we have for one protein, right? You have to show it for more proteins. And there's a database of alanine scanning experiments, so where the people exactly look at protein-protein interfaces and they mutate single residues to alanine, just like they did for this experiment before, and show hotspots. And Jan and I scanned the data set then, so this is exclusively hotspots now, accuracy and coverage for hotspots, and it appeared, so today that looks a little bit different, but then the data set, for 10% of all the data that we had, we predicted it correctly without making the threshold at which we made no mistake. And even in sort of in the worst case, we still had 60% right. Now, the major point here, well, we can predict hotspots, and that was a paper on its own. But the major thing really is it tells you something about the biology. So here you use machine learning. So you use machine learning to establish something in biology. Okay? No, it cannot be just a gradual scale. There is something special, otherwise you couldn't predict them. Because again, there's no machine learning that ever tried to learn them. There's no over-optimization. I'm testing the device on something that it had never seen. Okay. Yeah, she's funny. What is the most important thing? Again, this is how well it uses by using experimental structure. This is how it uses sequence evolution plus predicted structure, evolution only, hydrophobic moment only, sequence only. So you see how much different aspects of this contribute to the hotspot prediction. Now, the next idea was find competitive binders. You pick out the profile of the binders that you predict, and then you say something that binds like that protein will have similar binders. So I will simply take this like a motif, and will go out and find other proteins that have a similar motif, and assume that these other proteins with a similar motif, in fact, bind in the same way. No. Yeah, I'm afraid that we are going to have a shorter. We didn't have time today for food, and somebody is a rebel here. Let's cut it here.